Hello, welcome to Chapter 8. So we just finished learning about confidence intervals and predicting where the true population lies. Now we're going to move into hypothesis testing, where we have some data from a sample and it's making us question something about the true population that we may have been told or something that we've known for a while, and now we're starting to question that. So we're going to learn some definitions in this lesson, a lot of definitions, and how to state our null and alternative hypotheses. So a hypothesis is a statement regarding a characteristic of one or more populations. Hypothesis testing is a formal process based on sample evidence and probability used to test hypotheses. So three basic steps to hypothesis testing is making a statement regarding the nature of the population. Then you're going to collect some evidence, some sample data to test that statement. And then you're going to analyze the data to assess the plausibility of the statement. The actual test begins by considering two hypotheses. They are called the null hypothesis, which is what we believe is true about the population, and the alternative hypothesis. So the null hypothesis, we usually label that with an H0, is a statement of no difference between sample means or proportions, or no difference between the sample mean or proportion and a population mean or proportion. In other words, the difference is zero. What we believe about the true population is true. Okay. The alternative hypothesis is a claim about the population that is contradictory to H0 and what we conclude when we reject H0. So when we make our hypothesis statements, there are three parameters that we could be testing. And notice that they're all the population symbols. So mu, the population mean, we could be testing P, the population proportion, or we could be testing sigma, the population standard deviation. The only two that we're actually going to work on this semester are the population mean and population proportion. There are three types of tests that we could be performing. One is a right tail test, where we're testing to see if one is greater than the other, that we're greater than the proposed value. The second test could be a left tail test, where we believe that the proposed value is less than, or a two tail test that's just not equal to. So a greater than, a less than, or a not equal to. So let's just try to write some hypothesis statements. A medical trial is conducted to test whether or not a new medicine reduces cholesterol by 25%. State the null and alternative hypotheses. So this is a percentage. So my what I'm testing, my parameter is P for proportions. And your H0 is always an equal to what we think is true. And so we believe that it's 25%, or you could write it as a decimal as well. And then the HA is what you're thinking that's contradictory. And so they think it's just whether or not it reduces. So reduces the cholesterol. So it would be a less than 25%. Does it reduce? Okay. Example 2. Active management labor is a group of interventions designed to help reduce the length of labor and the rate of cesarean deliveries of babies. According to a recent article, the average cost of having a baby in a U.S. hospital is $2,528. A random sample of 200 AML deliveries had a mean cost of $2,480 with a standard deviation of 766. Do the data provide sufficient evidence to conclude that on average, AML does reduce the cost of having a baby in a U.S. hospital? Write the null and alternative hypotheses in symbols. State the type of test. So one thing we have to know, this would be like a whole problem right here, is when we're stating the null and alternative hypotheses, we don't care about the sample data. That's just the evidence that we're going to use in court, basically. So we don't really care about that. So we want to know what parameter are we testing? We have a unit of dollars, so we're testing quantitative data or means. And remember the H0 is always an equal. And what we think is true about the population was the $2,528. And they're proposing, it says, do the data provide sufficient evidence to conclude that it reduces? So again, it's another less than. And notice that my parameter value is still the same. So your parameter symbol is the same, your value is the same. It's just your H0 is always equal to, and your HA is either less than, greater than, or not equal to. Example. On a state driver's test, about 40% pass the test on the first try. We want to test if more than 40% pass on the first try. Write the null and alternative hypotheses and symbols and state the test. Okay, so we have a percent sign, so that tells us that we're dealing with proportions. And your null is always an equal to. We believe that it's 40% is the true percentage. And it just says we want to test if more. So if more tells us that we're testing to see if it's a greater than 40%. Okay, so that's basically our first step in hypothesis testing. We're going to actually break down this hypothesis testing into 6 steps that we're going to do. And this is our first step, writing a hypothesis. So our second step has to do with what type of errors could we have. So we're going to look at types of errors. So we could have what's called a type 1 or a type 2 error. And we're going to talk about what they are and how we find them. So on this part of my little 2x2 box is what is actually true in real life, okay? What is actually true in real life up here. And then over here is the action, what actually happened by, we'll say, the jury. Okay, so we're thinking of a hypothesis test is like the person's not guilty, and then HA would be the person's guilty. Okay, so there's 4 possible outcomes in this table. So up here is we could have, it's true, the person is actually innocent in real life, and the jury did not say that they're guilty. Okay, so that's a correct outcome. They were really innocent, and the jury did not say that they were guilty. That is a correct decision. We can also have where the person is actually innocent, but the jury found them guilty. That's right here. The jury found them guilty. So the jury finds them guilty and they're innocent. That's a type 1 error. That's going to be our alpha that we're choosing. Okay, we want to keep this small as possible. You want to keep that error small. You don't want to have innocent people being found guilty. That is a type 1 error. The third situation here, so this is 1, this is 2, this is 3. The third situation could be the person is actually guilty. Remember, this is actually in real life. They're actually guilty, but the jury found them not guilty. That is also not a good situation. They are guilty, but the jury found them not guilty. That's the type 2 error. We call that beta. Okay, that's beta. We're not going to worry too much about beta in this class, but just understanding that it is the type 2 error. So that's number 3. Then we could have our last possible outcome where the person is actually guilty in real life and the jury did find them guilty. And that's a good outcome because we do want people that have committed crimes to have to pay for their crimes. That would be guilty and found guilty here. So I just want to go over alpha is this, it looks like an A, but it's really like that. And it's pronounced alpha. It's our probability of a type 1 error, which by definition is the probability of rejecting the null hypothesis when the null hypothesis is true. Okay, that's saying they're guilty when really they're innocent. Beta is the probability of a type 2 error, and that by definition is the probability of not rejecting the null hypothesis when the null hypothesis is false. And so that is when they're actually guilty, but the jury says they're not guilty. So ideally, we'd like to keep both alpha and beta as small as possible. Rarely could they ever be zero, but we are trying to keep them as small as possible. And we're really only able to kind of control alpha with what we're working with in this class. So let's look at example 4. So example 4 says, suppose the null hypothesis H0 is the tire was made and inflated at the correct PSI of 32. And we're going to say the type 1 and type 2 errors here. So the type 1 would be the tire was inflated at 32 PSI, but the tire was made and inflated at 32 PSI, correct, but maybe the testing tool said it wasn't. Okay, so H0 is true, but they say it's not. Type 2 is the tire was made incorrectly, not at 32 PSI, but the testing tool said it was fine. Okay, which error has a greater consequence? That's a great question. So let's say we have type 1 error. The tester, probably the quality control person, uses a little tool on the tire and they say it was not inflated correctly, and they, check it and they send it back for whatever reason. There really isn't a consequence. Now they are maybe going to throw away that tire or have it rechecked or something, but the type 2 error says the tire was made incorrectly, not at the 32 PSI, but the testing tool said it was fine. So the greater consequence in this case is the type 2, because that means that the testing tool said it was fine. They passed the tire on to maybe a dealership, Firestone or whatever, and then they go and sell the tire, and the tire is not inflated correctly, and the person gets the tire on their car and it could cause an accident. So in this case, the type 2 error is the worst of the two. Let's look at example. Example 5 says, a certain experimental drug claims a cure rate of at least 75% for males with prostate cancer. Describe both the type 1 and type 2 errors in context. Which error is the more serious? So type 1 is rejecting the cure rate when it really is 75%. when it really is 75%. Okay, so saying it's not going to do a good job. So maybe people wouldn't take the medicine if they don't really think it is going to cure it at 75% because they rejected it. Type 2 is accepting the cure rate when it actually is not 75%. Which error has greater consequence? This one is a tough one. There are consequences for both situations, unlike the last example. So for type 1, somebody might decide to take a different drug if they were told that the cure rate was really not 75%, even though it really was. So they could be missing out on a drug that is really going to give them a high success rate. However, I believe type 2 might be the worst one in this case as well, because type 2 says accepting the cure rate when it actually is not 75. So that means somebody is starting on this medicine because they've accepted the cure rate. They're like, oh, yep, it's good. They start on this medicine when in reality it's not good. And maybe their cancer progresses in a bad direction. So I would probably say type 2. This one is a hard one. I think you could negotiate a reason for choosing either. Okay. So let's look at the last example in this first part of 8.1, example 6. Determine both type 1 and type 2 errors for the following scenario. Assume a null hypothesis H0 that states the percentage of adults with jobs is 88%. Okay. Not to reject the null hypothesis that the percentage of adults who have jobs is 88% when that percentage is actually less than 88%. So you don't reject H0 when it really is not true. That is a type 2 error. B says not to reject the null hypothesis that the percentage of adults who have jobs is 88% when the percentage is actually at least 88%. Okay, so don't reject when it's at least what they say it is. So that would be a correct decision. Let's look at it says reject the null hypothesis that the percentage of adults who have jobs is 88% when the percentage is actually 88%. So you reject the null hypothesis when the null hypothesis is actually true. So that is a type 1 error. Okay. So we're going to talk about distributions here. Catch me back for the second video, and we're going to start talking about distributions.